So we are going to continue. So we just had this thing that the ratio of the thing is that in the case trivial case of here n is equal to n, or in case the ratio of n and n are infinite, they are very small. So the result trivial case. It will correspond to how we have our definition of how we can have a state and our measurement of the state, which is different. But in case of probabilities, other probabilities where n will be large or n will not necessarily be infinity. So how the idea of these probabilities, which is basically sort of quantum probabilities, which is probabilities, which is an interpretation where which is specific to the measurement which we are observing. Sorry, which is called a frequentistic probability interpretation. So it may not cohere with that. So if it's not cohere with that, or further, if I just if we say that the other states where n is not ratio of n may not necessarily be infinity, or they may not be equal to one. So if we can have we have to solve our problems to show that this state, our state psi n, which we normally write as C1, C2, Cn, exponential of iota phi 1, phi 1, this iota phi 2. These are the phases involved, take into phase into consideration that state. There, so the phases are involved. So that frequentistic interpretation of probabilities, when it's coupled to these states, that becomes inadequate. So, for example, for nearly not n, for almost closer to n, we can have this formula. It can be somehow there can be an approximate formula to it where this state, this state, this state, where psi n1 and 2 and n. So it can be somehow we can have a more or less the state can be written as like this. We get this Cm square outside the bracket 1 minus Cm square divided by n. So it's equivalent to 1 by 4 n. So you can have a nearly true state equation where this probability of this state for these states, where these individual states are factored by these phase factors. So total probability normally it should come out to be Cm square is equal to 1 for large n, for n, but for large or n very large or n tending to infinity, not infinity exact. So this interpretation, this formula can have this approximate formula. So let's get the proof of this formula. Is there in the book? You can see it. It's not that complicated. So if it is like that, then therefore any state phi for any state phi The norm pi denotes this. So pi may be any state, the base size. So for the frequency operators, so you can check the proof of this thing in the subsequent steps. And the normalization condition is given by this. And sine approaches eigenstates or the frequency operators Pn, where n goes to infinity. N is not sometimes large, or they approach they do not approach any limit. So in the extreme cases, they n is equal to n, or n goes to infinity. So these are two limits. The other probabilities, the weight of other probabilities, they may not necessarily approach to any limit. So there can be, what can be the size of the Hilbert space in that sense. So there, physicists like Hartle, Goldstein, so there is a reference there. So you can, what should be the size of the Hilbert space? It's also a question. Vis-a-vis these chosen probabilities where the states are supposed to be large. Not large in the sense of they are large, they are infinite. So they are large. The set of large states which are identified with these state size. So for them, how big should be that? How large should be that Hilbert space? And construct a Hilbert space which is for infinite dimensional Hilbert space. Show that operators. Pn acting on this space and eigenvalues SCM square. So it becomes a stretch of imagination that it should also hold for when n is infinite or infinite dimensional Hilbert space in the way we define Hilbert space. So what we are going to do, we are going to strengthen the version of postulate about eigenstates and eigenvalues, assuming that the normalized state of the psi is nearly eigenvector of the Hermitian operator. In the sense that we are going to make norm of a minus a psi is small. Then the state represented by psi is almost certain that the value of observable representing A should be closer to A. So we make it norm of A minus A small so that this will be closer to A. But an eigenstate has a different eigenvector associated with it. So we are going to make the norm small so that our definition corresponds to this. So again, here, when we say we're going to make it small, so we are somehow implicitly getting into the notion of probabilities. How small should we use probabilities? So again, we have a subject to bias of those probabilities of assigning relative weight to those specific measurements. So you cannot do away with it on this. So and apart from these, so this is that again when we assume that ratio n by n, so it should be small. So either it should be 0 or it will the first two cases, but it is assumed to be small. So probability of observing if you assume that he is observing the wrong value of the probabilities, so what at the end it should somehow verify, and if those are small, they should add up to somehow assume that at the end they should verify. It should be equal to 1, or it should verify Bohr rule. So again, it's a question: should we assume that the prior existence of Bohr rule as a truism, or Bohr rule can be verified from these approximate assumptions. So this is also a sort of it's a sort of open scope space where things cannot be defined in black and white. So, further, what we are going to say is that this probability phi on side, where phi are the orthonormal eigenvectors E with eigenvalue. So these are objective probabilities, and they do not depend on the presence of the observer. So now what to do away with these things, what we are going to do, we will turn to other broad class of quantum mechanical interpretations, where the idea of state vector closed system gives a complete account of the state. So instead of, so a closed system will give us a complete account of the given state. Instead, there will be a description of probabilities. So for that, what we have to do, we have to reinterpret this open other interpretation vis-a-vis these probabilities. The interpretation is how we have to interpret it in the sense that, so instead of invoking this collapse or mysterious collapse, what we are going to do is that so the state is normalized at the side probability of system actually psi should be a quantity represented by Hermitian vector A. So psi, state vector psi, represented by Hermitian vector, Hermitian operator A with eigenvalue an, that's fine. So we assume that these are objective probabilities. So they will not depend upon the observer or the state of the observer or the state of the system or the state of observer in interaction in case of this Schrodinger cat being dead, interacting with the system. So it will depend not on so they will have these probabilities in the objective. And if they are objective and the probability is assigned like this, where phi are the orthonormal vectors of E, the eigenvalue E. So if you assume that probabilities are objective, and we have to reinterpret these overall interpretations for closed systems, in which Bohr rule has not fundamentally verified. But if you assume then probability is defined by this, then phi is the orthonormal eigenvectors with eigenvalue E. So in that case, what we are going to say is, so so what we are going to say, as I said, so what we are going to say is what is being measured that the observable things has been found. Probability of that the observable thing that quantity being measured as a value n. That's fine. So if you do not give up significance of state vector, then we are not forced to accept the reality of the huge number of worlds contained by. So if you do not, so that means if you do not give any other significance to the state vector, then we are not forced to accept the reality of huge number of worlds. So if you do not give away that state vector has any other significance. So we are not necessarily forced to accept the many worldview of quantum, or we are not going to accept or reject either of these. It can be ambivalent. So of course we can also give up, but the thing is that we can give up this born probability issue. That interpretation has to be given up. So this sums up our discussion. But now we are coming to, at the end, we are coming to a very an interpretation of quantum mechanics which has been very much talked in literature and which has been pioneered by many physicists, which include, uh, which also called, first was Copenhagen, then there was many more. So we are going to add to this pretty deep coherent histories. So the background is also the way whether the system is open or closed, because the system, if it's not closed or whether it's open, so the idea of phase factors, where the system is isolated or insulated, because the system is not is fundamentally decoherent. So the idea of environment somehow has something to do with how the state is constructed and the measurement of that state. Now the thing is that we are not interested in the decoherent histories. We'll take the part of the histories are coherent in that sense. So how should we make a system decoherent histories, not coherent systems, decoherent histories ought to be made consistent. That's the point. Decoherent histories have to be have a consistent interpretation. So this thing has been advocated by many people, Greeks, Holmes, Horton, Hawking. With this fifth, he has also written an interesting book, Consistent Quantum Mechanics. So which propose this consistent interpretation. So how these consistent interpretation has to be taken into account from this decoherent histories. So that's a job what we do at least conceptually, and we assume that the quantum mechanical thing runs like that. Our conceptualization of decoherent histories in a consistent manner will have a quantum mechanical interpretation of the universe or the states. And which attribute probabilities that are consistent with the usual properties of the probability. Now here, what we are going to do is, so we'll say what is the history. The history in the classical sense is that normally the classical mechanics or classical interpretation, particle is a continuous history. So there is no cut. But once we have quantum mechanics, that history has to be just somehow made malleable with probabilities, and those probabilities are adjustable to different histories. And there is not a history, one clean history or one particular history. You can have average histories or average probabilities which will chart down the state of a particle or particles. Now the question here is, so here how we define the consistent histories, consistent decoherent histories, which might have a consistent, which is going to have a consistent interpretation. So a history, here the history is characterized by normal state style, normal state style. So it will evolve from initial state, evolve from initial time t0 to time t1. So according to time independent, according to time independent Schrodinger equation. So and the system is averaged for its properties, holding only fixed values a1 n for observables a1 n. Now, which is followed by evolution to time t2. Now holding values a to n for a to n, and then for t3 in the same way then a3n to a3n, so t4, so on and so forth. So you will have a state, normal state size, which evolves from time t0. So state size will evolve from t0 to t1. Then what we are going to do? We are going to hold only fixed values of a1 n for a few observables. So once we do this procedure, then again we are going to hold fixed values a to n for a few other observables. So we are going to fix or at every stage or every stage in the process, and in the sense we are going to construct the whole system. That is, history is defined by the state psi by the times t1, t2, given by the values a1 and a2 n. It's the observables that are held by each parameter. So they correspond to the observations carried by the particle trajectory, not us. So if you want to simplify this notation, then psi can be written as psi a1, a2, an can be written as, you write it here, lambda n exponential of an of iota h tn minus 1 minus tn minus 1, sorry, divided by h. So this is the first step, tn minus tn minus 1. So it's being multiplied by here, multiplied by the second term. This is continuous expression. The second expression you can find it minus iota h. If it's n1 n2, it's d3 minus 2 h, d3 minus d2 by h into this lambda n. Now lambda 2 is exponential of minus iota h, d2 minus d1 by h. This we can see is from the descending sense. t3 minus t2, t2 minus t1, and at the end we will have lambda 1 exponential of minus iota h. So at each stage we are going to fix some of them, so not all for these, to make it consistent. So if we do this way, where lambda 1, so here lambda 1 a, lambda 2 a, are the sum of projection operators. So we have to which are consistent with the restrictions labeled by A1, A2. So you remember that projection operators A dagger is equal to modulus of A square. They can sort of idempotent property. So they will come to 5 diagram, 5 diagram. Over an observer lambda A would be sum of this over an orthonormal states phi. They are complete in the subspace consisting the eigenstates. This AR of eigenvalue ER. So this method is called coarse grain, as has been advocated by Horton and Gelli. So the use of a projection operator that it will come to its state as if. So you can also use this sign states. So if you want to write it in that sense, which will make it more clear this thing, that psi A1, A2, AN is once I enter implications by N by H, then the N, A N, P N, then B2, A2, D2, lambda 1, A1, B1, N0 by H psi. Where lambda or A or P are the sum of projection vectors, which is in the Heisenberg picture. Where lambda or is lambda or. So we can now have a Heisenberg picture, which is where lambda r is given by this. So psi state can be represented. Lambdas are different states. This is one state. This is another state. This is the other states. These are consistent states which have been taken over probabilities in a certain range, such that at the end they will have a consistent interpretation, and they will have each has a decoherent history, such that the probability of this will be given by so the probability will be given by probability of this will be given by So these probabilities are basically they are objective histories. So they are, so it does away with the notion of subjective. Then the idea of this pointer probabilities, the specific frequency interpretation of the probability that the measurement will depend upon the subjective choice of the observer who is going to measure, and that choice has the role of measurement observer as well as sometimes the instrument also, which apparatus which is going to measure that state psi. So and the observer this it will be subjective, but here this directly we have an objective interpretation of objective probabilities are called objective properties of objective properties objective it's more or less of various histories objective properties of various histories, and not necessarily as seen by the observer. So it's not observer specific or it's not subjective, that's it. So, in some sense, the objectivity is somehow sort of restored in this interpretation as such. So the question is specifically how can we show that probabilities for all possible values and one of the observables equals to the history of which the observer is not held fixed. So there is uh, to further show that this is an objective history, we have just show an implicit assumption which comes out to be we have to show that the sum of probabilities over all possible values of one of observables, say of AR equals probability of history, so in which the point where it's not held is not held fixed. So there is an indirect assumption that to show that sum of probabilities over all observable possible, that we have to show that the value where it's not held fixed, one observer can take all other possibilities. One they can contain the sum of all possibilities or probabilities. So for that, the consistency conditions should be that psi of A1 prime, A2 prime, AN prime, and psi of A1, A2. This inner product should be 0, where A1 prime is equal to A2, A2 is equal to A2 prime, and so on and so forth. Such that the consistency condition is basically so for the thing that so there comes an indirect point from this that if it's not held fixed, then each observer should take all a particular observer which is not held fixed should take the sum of all values in these probabilities. So for that, it should satisfy the consistency condition, which is that A1 equal to AR minus 1, AR plus 1, AN is equal to psi of EN into. So it's a sine side, and these two sides, which will take values in the so sort of a normalization condition where lambda is this ART is equal to 1 and this is equal to this. So the point is that the history is so such that a probability of A1, A2, and En psi of psi is. The history is that satisfies consistency condition. This that satisfies the consistency condition. This is a consistency condition. If it satisfies this, then it is identified by the conditions of decoherence. This is identified by the conditions of the decoherence. So here there is a particular example which the book has chosen from classical mechanics that is given a particle which is having a motion around, so it will not fundamentally change its orbit from one state to the another state. By the application of some fields, it will be there around there in that sense. So the perturbations in the planets do not allow a planet to move from one to another orbit, but they will allow some changes. and the averaging over the perturbations thus destroy the correlations. So that will those will invalidate the consistency conditions. Yeah. So what Weinberg is saying that there is nothing consistent or absolute about that. Probabilities or intercurrent histories approach state vector will be only served as the predictor of probabilities or state vector, but it doesn't describe exactly. It doesn't give the complete description of the system, and which echoes a sort of that. Classical that thing that we should be able to somehow determine a given state of the system or our objective interpretation of the world which we are going to have. Or derive a Bohr rule at the end. We would assume it, we should arrive at it. So these are some implicit assumptions of these histories, different histories, and a consistent interpretation of a given state to psi. So there can be, so for Weinberg, so if you just include the point of Weinberg in this thing that he's of the opinion that which is not necessarily shared by many people, that there is no interpretation of quantum mechanics that doesn't have a serious flaw. That's fine. And we ought to take seriously this possibility of finding some more. So Weinberg is going for a more optimistic to have a satisfactory interpretation of quantum mechanics from a more fundamental theory for which it's a suitable approximation. So there is an impending optimism shared by Weinberg, not necessarily shared by other interpreters of quantum mechanics who are that one or other who may be converted to one or the other point of view as far as the quantum mechanics interpretation of quantum. What will constitute fundamentally as quantum mechanical reality in that sense. And this further debate can be also just extended to larger questions. What do you mean by objectivity and subjectivity slash? What do you mean whether determinism and interdeterminism as a construct, uh, which is related to objective constructions. So deterministic slash indeterminism, consistent slash inconsistent in this case, and objective slash subjective interpretations, relativist probabilities, frequentist probability interpretation when compared to the other interpretations of probabilities. Uh, when coupled to how we have described the state vector, and those probabilities are definite or their value is specified by the observer in consideration. So he is filtering data in the not in one universe but in the many universes. But we have also we can also incorporate the idea of meta observer or super observer in this entire discussion also. So for him, the observer, the born rule, how we can see it? Can be observer, meta observer, or super observer? So we will not have a scattering matrix. We can have a scattering matrix. So these are different interpretations. So this completes our this chapter of general principles of quantum mechanics. Hope you enjoyed it. Thanks.